Let's take a look at section 9.3, and 9.3 is on looking at confidence intervals. We're still using confidence intervals just like we did back in chapter 7. The concepts are all very, very similar. The only difference is now we're looking at estimating the mean of a population rather than a proportion that goes with the population. So what's going to be different this time is we're looking at what's called a t-distribution. So a t-distribution is very similar in shape to a normal distribution, but it's got a few properties that are a little bit different. So hypothesis tests and confidence intervals that we use when we're estimating the mean of a population are called the t-distribution, and the statistic, instead of calling it a z-score, this time we're going to call it a t-score or a t-statistic. But the idea is all the same. We still have to calculate that test statistic. We call it a t-statistic this time instead of a z-score. And the formula we're going to use is very similar to what it was for z-scores. We're going to use x bar minus mu divided by the estimated standard error. And then the estimated standard error, this time we're going to use S divided by the square root of n. N, of course, is still our sample size. However, we don't know the population standard deviation most of the time. And so for that reason, we have to use S. S represents the sample size. Let me just write that down. S, of course, is the, I'm sorry, not sample size, sample standard deviation. So sample standard deviation. So since population standard deviation sigma is almost always unknown, we're going to estimate what we think the standard error is using the sample standard deviation instead. The t-statistic doesn't follow the normal distribution because the denominator changes with every sample size. However, it's very similar in shape and has a lot of the same properties, which we're going to talk about in just a minute. The t-statistic is a little bit more variable than the z-statistic that we're used to. If the three conditions of the central limit theorem are met, then the t-statistic follows a distribution that we call the t-distribution. And we're not, honestly, I'm not going to have you do a whole lot with the t-distribution directly. We're going to use StatCrunch to figure a lot of this stuff out. So don't get too overwhelmed by the new information. I want you to think big picture here. We're still estimating a confidence interval, just like we did back in chapter 7. That's really, the principle of that is not going to change. So a few properties of the t-distribution. It's still symmetric in bell shape, just like the normal. The tails on the outside tend to be a little bit thicker than the normal distribution. The shape, however, depends on the sample size, which depends on something that we call the degrees of freedom. And you may see that we abbreviate that DF. So if you see DF, that's what we're talking about. If DF is small, then the tails are going to be thick. And if DF increases, then the tails are going to get a little bit thinner. As DF approaches infinity, so in other words, as the degrees of freedom gets larger, then the t-distribution approaches a standard normal distribution. So remember what this notation means. This is a normal distribution with a mean of 0 and a standard deviation 1. So here we'll note that. This is our standard normal distribution, just like it was earlier in the course. Okay, so let's keep going here. Couple of pictures here to give you an idea of what we're talking about. In this first picture, we've got this n 0, 1. That's our regular standard normal distribution. Below it is the t-distribution with degrees of freedom 1. So you can see it's similar in shape. It's not quite as tall, and the tails are just a little bit thicker. In the next picture, we've got the standard normal distribution again, but this time we've got the t-distribution with degrees of freedom of 10. So what I want you to see from picture A to picture B is how the t-distribution, now that we have a higher degree of freedom, got closer to the normal distribution. It's almost on top of it. There's a little bit of a difference. It's still, the t-distribution is still a little bit shorter. Tails are still a little thicker, but it's a lot closer. Now in picture C, what's happening? We've got a t-distribution with degrees of freedom of 40. So as the degrees of freedom gets larger, you can see that we approach the standard normal distribution. It's almost exactly the same. Just looking at it, it's really hard to see what the difference is. All right, so let's talk a little bit more about confidence intervals. So remember what confidence intervals are. Confidence intervals provide us with a range of plausible values that tell us something about the population parameter. So let's see what they want here. Confidence interval, I think is what they're looking for. Confidence interval can be interpreted as a range of plausible values for the population, and leave you much room here, the population parameter. And in this case, the population parameter we're going to estimate is the mean. Okay. The confidence level, so remember like 95, 99%, 80%, whatever, confidence level is a measure of how well the method used to produce the confidence interval performs. So remember we had some questions, I think it was maybe last week, I don't remember exactly when it was, but we had some questions where we said, if I were to repeat this 100 times and it's a 95% confidence interval, how many of those samples would we expect, or how many of those confidence intervals that we develop would we expect to include the actual population proportion? And we'd say 95 if it's a 95% confidence interval. So whatever the level is, that gives us an idea of how well our method is that we're using to estimate whatever the population mean is. So when do we use a confidence interval? Whenever you're estimating the value of a population parameter, and again, in this unit, it's the mean that we're estimating on the basis of a sample statistic. So when we don't know what the population mean is, but we take a sample and we measure the mean on that sample, that's our sample statistic, we're using that to estimate the population parameter. So in this case, the sample mean is going to be used to estimate that population mean. For example, what is the typical time a Flagler College student studied per week? So I guess time meaning like number of hours the students studied per week. We don't know how the mean number of hours all students studied per week. So what we might do is pull a random sample of say 25 students or 50 students, estimate the population mean based on the sample mean. Do not use a confidence interval. Let's see what they're looking for. Do not use a confidence interval if there is no uncertainty in your estimate. If you have data for the entire population, then you don't need to find a confidence interval since the population parameter is known. We only use a confidence interval when the population parameter is not known and we have to estimate it using a random sample. Okay, again, this should not be anything new. This is exactly what we did in chapter 7. Same concepts. The only thing that's new is we're looking at means instead of proportions, but everything is the same idea conceptually. So what are the conditions for the central limit theorem to be met? Similar to what they were in the previous part of this chapter. Actually, I think it's the same conditions we used in section 9.2. It's got to be a random and independent sample. The sample has to be large enough so that either the population is normal. So if you have a small sample and they tell you the population is normal, you're good to go. It doesn't matter what the sample size is. Or if we don't know anything about the population, or maybe the population is not normal, the sample size has to be at least 25. So n has to be greater than or equal to 25. And then the population has to be large, just like it was in the previous section. How large does the population need to be? At least 10 times the sample. So at least 10 times larger than whatever the sample size is. All right, so let's take a look at this example. A used car website wanted to estimate the mean price of a 2012 Nissan Altima. The site gathered data on a random sample of 30 such cars. So I'm going to write a few things down. The sample is 30, so that means n is 30. It found that the sample mean of 16,610. So my sample mean would be x bar. You need to get in the habit of writing these things down. When you read the question, use the correct symbol so you can keep everything straight. So the mean for my sample, x bar, is 16,610. And then I can calculate the standard deviation on my sample standard deviation. That would be S, is 2736. The 95% confidence interval for the mean cost of this model car based on data is, remember what a confidence interval looked like. You've got a lower bound followed by an upper bound. So the estimate for the mean cost for all Nissan Altimas is given by this confidence interval. So it says describe the population. So who is the population? That would be all 2012 Nissan Altimas. Okay, so all 2012 Nissan Altimas is who we're interested in measuring. Identify the following. All right, so the 16,610, we said that was x bar. And so because it measures the sample, that makes it a statistic. 2736 would be S, and so that measures a sample as well, so that's a statistic. And then N equals 30 was our sample size, also measures a sample, so that's a statistic. Verify the conditions are met. They said it was a random sample, so we are good to go there. Is the sample large enough? Yes, because it's greater than 25. Our sample was 30. And of course, the population of all Nissan Altimas should certainly be more than 10 times 30, obviously. So that condition is met. All right, interpret the confidence interval. So this was a 95% confidence interval. So what we're going to say is we're going to say we are 95% confident that the mean values of the car. We were looking at trying to estimate the mean price. So the mean price of all 2012 Nissan Altimas is between what two numbers? We don't know exactly what it is, but we think it's between what two numbers? We think it's between 15,588 and 17,632. Okay, so we think the mean price for all Nissan Altimas is somewhere between those two numbers. So based on that, is it plausible that the population mean is 18,000 based on this confidence interval? Well, no, because that's not part of our confidence interval. So we're going to say no, since 18,000 is not captured in our confidence interval. And that's basically it. It's not captured in our interval, so no, that's not plausible. That's not a realistic value. It's not plausible based on our interval. All right, so a 95% confidence interval means that if we were to take 100 random samples of the same size from the population, we would expect 95 of them, right? So 95% of 100 would be 95, right? 95 of them would contain the actual population parameter, and 5 of them would not contain the population parameter. So if we were to repeat this over and over again, if we were to do 100 times, sample, 100 times, samples of size 30, 100 times over and over again using the same method, and then we were to create a confidence interval for each of those individual samples. Of course, the confidence interval is going to shift, right? Because each individual sample, the mean is going to shift depending on what I pull for that sample. But 95 of those 100 samples we would expect would contain the true population parameter, and we think 5 of them would not. And that's really what we mean when we say 95% confidence level. Let's talk a little bit more about how to actually do this by hand. So the one sample T interval is a confidence interval for a population mean. And we're going to do this in StatCrunch as well, but I want to show you quickly how to do this by hand. Before we get too into this, I just want to remind you, back in Chapter 7, how did we do a confidence interval? We did p hat plus minus the margin of error, if you remember that formula. Really, it's the exact same idea. It's the same formula, basically. We're just not using p hat. Instead, we're using our sample mean. So our formula is going to be x bar this time plus minus our margin of error. It's the exact same structure. Nothing has changed conceptually. And I think it's really important that you see the parallels between what we're doing now and what we were doing earlier in this unit. Now, what is different is how we're going to compute that margin of error. So in the previous part of the unit, when we were doing proportions, the margin of error, if you remember, was z star times the standard error. And we used the estimated standard error back in Chapter 7. So this time it's going to be, the margin of error is going to be, we're going to call it t star times the estimated standard error. Exact same thing. The only difference is instead of z star, we're calling it t star because we're using a t distribution. But the structure is the exact same. And the way we're going to compute that margin of error, it's a little different. This formula is a little different. Earlier in the course, remember, the standard error estimated was the square root of, we used p hat times 1 minus p hat divided by n. If you remember, that's what we used back when we were doing proportions. Now it's going to look like this. It's going to be that formula we had earlier in the notes. It's s divided by the square root of n, where s, remember, is your sample size, n is your, I'm sorry, scratch that. S is your sample standard deviation, n is your sample size. Let's write that down. S is your sample standard deviation, and of course, n is your sample size. All right. So as I said, this is stuff we did back in chapter 7. The multiplier T star is a constant found using the T distribution with degrees of freedom. And the degrees of freedom, I know it's kind of a mysterious concept right now. Just kind of go with me for now. I'm going to give you a little formula here. Degrees of freedom is going to vary depending on your sample size. And so that's going to be how you determine which T star value to use. And that is going to be found using this little formula, n minus 1. This value T star tells us how wide the margin of error is. So how wide the margin of error is in terms of the standard error. It's this, like I said, it's very similar to what we used Z star before. Z star told us how far out to cover in our distribution, how many standard errors to include. It's the exact same thing. T star it tells us how many standard errors to include in our margin of error. All right, so in this example, let's look a little bit more at this T distribution. We'll investigate what happens to the T star multiplier as the sample size increases and the level of confidence stays the same. So we're going to use StatCrunch to do this. Now, I want you to pay very close attention in class. You're going to ask me how to do this. I'm going to tell you to look at your notes. This is the part of the notes I want you to pay attention to as far as the directions for StatCrunch. These are what you're going to follow in StatCrunch. You're going to go to Stat, Calculator, and then you're going to choose something called T, which is our T distribution. So I think I have a window open here. Let me show you what this looks like. So we're going to go to Stat, Calculator, and then down here to this T distribution. It looks very similar to a normal distribution. Remember, the shape is the same. What's different is the degrees of freedom, and that's what you're going to have to adjust in just a minute. So by default, the degrees of freedom is going to be set at 10. Change the degrees of freedom to 9 for a sample size of 10. So in other words, n is your sample size, don't forget. So degrees of freedom, if my sample size is 10, degrees of freedom will be 9, 10 minus 1. So yeah, let's see. Let me see what they want us to do with this next example. They're just giving us a basic one. All right, I'm looking at the chart here to see what they want us to fill in. Let's enter, it says enter 0.95 in the lower right-hand box. I'm trying to look at what they want us to do with this chart here. I think we're missing some directions in the notes here. This should say, let's see, so the 10 degrees of freedom is 10. It just says enter 0.95. Okay, I guess I see what they want us to do. So they're telling us start with 0.95. So I'm going to leave this at 10 for now. I'm going to click on between. And what I want to cover is 95% of the graph. So let me get rid of this. Let me get rid of this. And let me put 0.95 here. Oops. There we go, 0.95. All right, so let me click on compute. And it's giving me 2.2281 to 2.2281. Let me go back to the notes here for a second. They said change the degrees of freedom to 9. All right, so let me do that. Let me change the degrees of freedom to 9. Degrees of freedom 10 would mean I have a sample size of 11. If I want a sample size of 10, let's make the degrees of freedom 9. Okay, let's try that again. So let me get rid of these and let's change this to 0.95. So basically 95% confidence interval would correspond to these numbers is what they're trying to tell you. So in your notes on the chart here, where it says 95% confidence level with a sample size of 10, that means our degrees of freedom would be 9. And our T star value is going to be that number that we just got from StatCrunch, 2.2622. So let's jot that down, 2.2622. All right, let's do this again. I'm going to keep it at a 95% confidence interval for now. But let's change the sample size to 30. So if sample size is 30, that means the degrees of freedom will be 29. So let's go back to StatCrunch, and I'm going to change this to 29. And I'm going to get rid of these numbers again, because these numbers are what I'm trying to determine. I'm trying to get the multiplier T star value. I'm going to do a 95% confidence interval again, and I get a value of 2.0452. That's the number I'm going to use here. So 2.0452. And let's go ahead and do 100, which means the degrees of freedom would be 99. I'm going to skip the details here on StatCrunch because what I really want you to focus on is what these numbers do and not what you're putting into StatCrunch right now. That's not the important thing with this example. So let me just give you these multiplier values. This would be 1.9842. What would the degrees of freedom be if I have a sample size of 500? That would give me 499 for my degrees of freedom, which gives me a multiplier of 1.9647. Again, don't worry about how I'm getting this. We'll give you these numbers, so you don't need to worry about that. I just want you to see the pattern here. If sample size 1,000, my degrees of freedom would be 999, and my t-star value for that would be 1.9623. So what happened to the degrees of freedom as the sample size increased? Of course, it did the same thing, right? As the sample size got larger, the degrees of freedom got larger as well. So degrees of freedom increased as well. What happened to the t-star multiplier as the sample size increased? So what I'm hoping you notice here with these numbers is the t-star multiplier is getting closer and closer, especially down here. The t-star number is getting closer and closer to a number that we used earlier in the course that looked like this. Remember this number, 1.96, which we had said, remember, was close to 2 when we used the empirical rule. That's what I want you to notice here. And the reason that's occurring is because, remember, we said as the degrees of freedom gets larger, the t distribution gets closer and closer to a standard normal distribution. So a 95% confidence level should get closer and closer. The multiplier should get closer and closer to this 1.96 number, and that's exactly what it's doing here. So let's write that down. So the t-star value approaches 1.96, which, as you recall, let's see, which is the z-score value for a 95% confidence interval with population proportion. So just like we were doing earlier in the course. All right, so continuing with our example with the Nissan Altimas. A used car website wanted to estimate the mean price of a 2012 Nissan Altima. The site gathered data on a random sample of 30 such cars, found a sample mean of 16,610 and a sample standard deviation of 2736. So identify the following. All right, what is our sample size? That should be pretty easy by now. N is equal to 30. Our sample mean, the symbol for that would be X bar, and so that was the 16,610. And then the sample standard deviation, which would be lowercase s, is 2736. All right, so then our t multiplier value. All right, so where can we get this t multiplier number? Now, if it's in the chart, we can use the chart. If it's not in this chart, we can also use StatCrunch to get this, and I'll show you how to do it in a minute. But we actually can use the chart because we're looking at a sample size of 30. So, and a 95% confidence interval is what we're interested in. And so in a second, we're going to be interested in. So my sample size is 30. My multiplier is going to be this 2.0452 number. So let's write that down. 2.0, what did I just say? 2.0452. And if you want to make a note, see chart above. And like I said, if we have a sample size that's different, that's not in that chart, we can certainly use StatCrunch to get that t-star value. So I'll show you that in a minute. Calculate the standard error and the margin of error. So our standard error, remember the formula we had earlier, our standard error is going to be our sample size, or sorry, I keep saying sample size, sample standard deviation divided by our sample mean, square root of our sample mean. So our sample standard deviation was the 2736, and we're going to divide it by the square root of 30. And so I said divided by the square root of our sample size. I think I said that right. So I'll just show you what that is. I think I have that number calculated. I've got 499.52 is going to be our standard error. Our margin of error, okay, so what is our margin of error? That is t-star times the standard error that we just computed. So the t-star value is that 2.0452 number times the 499.52 that we just computed. So my margin of error is going to be 1,021.62. And so once you've got that margin of error, the confidence interval is a piece of cake. So remember the formula for our confidence interval it is X bar plus minus our margin of error. So X bar, remember what X bar was. X bar was up here. That was the 16,610 number. So we're going to take 16,610 and we're going to add and we're going to subtract the 1,021.62 that we just computed. So let me get those numbers. So 16,610 minus the 1,021.62 gives me a lower bound of 15,588. I'll leave the change in there. That's 38. And then my upper bound, if we do the same thing, we're going to add that margin of error to our upper bound. And I'm getting an upper bound of 17,631.62. And that's going to be our confidence interval. So we think we are 95% confident that the mean value or the mean sales price for all 2012 Nissan Altimas is somewhere between 15,588 and 17,631. All right, let's look at the next example here. It says a random sample of 35 college students was asked how many movies they had seen in the previous month. The sample mean was 4.414 movies, and the sample standard deviation was 8.02. Describe the population. So the population would be college students, right? So I assume we're looking at all college students. They didn't just say Flagler students or anything like that, so we'll just go with all college students. Identify the following. So the 4.14 is our sample mean, so that would be X bar, and of course that would be a statistic. The sample standard deviation was 8.02, so that would be S, and that would as well be a statistic. And then our sample size was 35, so that would be N, and that would also be a statistic. Assuming the conditions for a confidence interval for population are met, use StatCrunch to find a 95% confidence interval. All right, so let's go through the process of doing this in StatCrunch. Please remember these directions are here when you're ready to do this in the assignment. We're going to go to Stat, then we're going to go to T-Stats, one sample with summary. So let's do that. So I'm going to close this out. We're going to go to Stat, T-Stats this time instead of proportion. We're going to T-Stats, one sample with summary. So you're going to put in your sample mean, you're going to put in your sample standard deviation, and you're going to put in your sample size. So by putting in your sample size, that accounts for the degrees of freedom, and that's going to get us that T-star value. StatCrunch will take care of that T-star value for us. We're really not going to do a whole lot with the T-star values by hand. StatCrunch is going to do this for us most of the time, and as long as you know the sample size, you should be good to go. I'm going to click here. They asked for, I believe, a 95% interval, so I'm going to leave this at 95, and I'm going to hit compute. And here's what I get from StatCrunch. This is the important information right here. So let's go ahead and fill this in, this table. Let's go ahead and fill this in. So my sample mean, they gave that to us again, but we already knew it. It was the 4.14 number. 4.14. The standard error, again, StatCrunch has computed that for us. So the standard error right here is 1.3. I'm just going to say 1.36 when I round it. So 1.36. Now, degrees of freedom StatCrunch will give us, but you can tell what it is. Remember, it's n minus 1. So if n was 35, my degrees of freedom is just 34. And then StatCrunch goes ahead and does the lower limit and the upper limit for us. So the lower limit is 1.39 if I round it, and the upper limit is 6.89. So let's write those numbers down, 1.39 and 6.89. So interpret the confidence interval in the context of the example. We're interested in looking at how many movies on average college students watch in a given month. So we're going to say we are 95% confident that all college students watched, or I don't know if it's past tense or we'll say watch watch well, let's see, let's do watch between 1.39 and 6.89 movies on average per month. And I know it sounds a little strange because you're talking about a movie. You're not going to watch 1.39 movies. You're going to watch one, or you're going to watch two. I don't know, maybe turn it off halfway or something. But the reason it's that we have those decimals is because they're averages, right? So on average, per student, they watch between 1.39 and 6.89 movies in a given month is the estimate. We could round that. We could say somewhere between 2 movies and 7 movies, or 1 and 6. I think either one would be fine, but we'll stick with those numbers, 1.39 and 6.89 on average. All right, let's look at the next example here. It says the 95% confidence interval that you calculated in the previous page. So they're just talking about the example we just did. Find a 99% confidence interval using StatCrunch and add it to the following table. So I think, so 95% is using the same data we just did. So our 95% confidence interval, the mean was 4.14. The standard error, I believe we just did. Let me go back and find that from the previous table because it's the same data, 1.36. I'm getting it from the table above. And the degrees of freedom was 34. The lower limit was 1.39 and the upper limit was 6.89. Now, if I want to get the same information for a 99% confidence interval, let's go ahead and do that. Let's go back to StatCrunch, and you don't have to start over. Just go to Options, Edit, and then just change this here to a 99% interval. And here we go. So same sample mean, of course, that's not going to change. Standard error is 1.36 again, same thing. Degrees of freedom. What changes, of course, is the lower limit and the upper limit. So sample mean is still 4.14, 1.36 for the standard error. Degrees of freedom is still 34, but my lower limit this time is going to be, let's go back to StatCrunch, 0.44, and my upper limit is 7.84. So my lower limit is 0.44, there's a decimal, and 7.84, okay? So what do you notice? The first thing I hope you notice is that this is a wider interval, right? We have a wider interval. So that's exactly what happened earlier in the course. I'm going to skip the details here. I think you can see this. The second interval is clearly wider than the first interval, right? It goes out, the lower bound is lower than the first one, and the upper bound is up higher than the second one. So which interval is wider? The 99% interval is wider, and it's the same idea as it was earlier in the course. It's going to cover more of the sampling distribution, which means you're going to have a wider interval. So it says find the t-star value for a 95% and a 99% interval for a sample of 35. Round your answer to 3 decimal places. Let's see. I'm trying to think of the best way to figure this out. Let's see. Let's do this. All right, let's write down our sample size. So in both cases, the sample size was 35, which means our degrees of freedom is going to be 34. So remember that the margin of error was, when we write our confidence interval, don't forget, was t star times our standard error. I'm trying to think of the best way to figure this out without having to make you do too much work. Let's do this. Let's start with the 95% interval. Go back to your interval here. So for your 95% interval, so I'm looking at this interval right here. Remember the sample mean was 4.14. So think about your interval like on a number line. 4.14 would go in the middle. My lower bound was 1.39. My upper bound was 6.89. So if I asked you, what is the margin of error, just like we did earlier in the course, you would tell me it's the interval from the lower bound to the mean, or the mean to the upper bound, whichever way you want to think about it, it's the same thing. So for the 95% confidence interval, my margin of error is going to be, let's do the upper one. We're going to do 6.89 minus 4.14. And so let's get that number and figure out what that is. 6.89 minus 4.14 gives me a margin of error of 2.75. And you could have done the other one, you would get the same exact number. If you do 4.14 minus 1.39, let's figure that out. 4.14 minus 1.39, I'm getting 2.75. I'm getting the exact same thing. So, and you should, right? Those should be exactly the same thing. So it doesn't matter which one you use. So let's take that information. So the margin of error for my 95% confidence interval in this example was 2.75. So what I want you to do is do a little bit of algebra here. I'm trying to find this t star value. So if my margin of error is 2.75, my t star value is what I'm looking for. My standard error, I calculated. My standard error, actually StatCrunch calculated it. My standard error was this number right here. So I'm going to plug that number into this little equation here. So times 1.36. So to solve for t star, I'm going to divide both sides by 1.36. All right, divide that out. So I'm doing 2.75 divided by 1.36, and I'm getting a t star value of about 2.0221. So my t star value there is 2.0221. Let's do the same thing for the 99% interval. All right, so let's do this. For the 99% interval, I'm going to do the same thing. So I'm going to put 4.14 in the middle. My lower bound for my 99% interval was 0.44. My upper bound was 7.84. I'm getting this information from the table right here. So for the 99% interval, my margin of error, if I use this upper bound minus the mean, let's see what that gives me for my margin of error. I'm getting 7.84 minus 4.14, and I'm getting a margin of error of 3.7. And again, I could do the same thing with the lower bound. I should get the same number. I'm going to skip the details, but we'll go with 3.7. So let's write this over here. So then for the 99% interval, remember, your margin of error is t star times your standard error. Okay, the standard error. So my margin of error I just computed, that was 3.7. My t star is what I'm looking for, and my standard error, same number right here, 1.36. So times 1.36. I'm trying to solve for t star, so I'm going to do some algebra. I'm going to divide by 1.36. And so 3.7 divided by 1.36. Let's see what that gives me. I'm getting a t star value of 2.72, it looks like. 2.7206. So it says, since the t star multiplier for the 90, which one of these is larger, 99% interval or 95% interval? Hopefully it's the 99% interval you see. So since the t star multiplier for the 99% confidence interval is larger than the t star multiplier for the 95% confidence interval, the 99% confidence interval is wider than the 95% confidence interval. It's exactly the same as it was back in chapter 7. The higher the level of confidence, the wider the interval. So that's what the next box says. Recall that from section 7.4 that the higher level of confidence results in a larger margin of error and therefore a wider confidence interval. Okay. All right, let's take a look at the next example. The 95% confidence interval that you calculated on the previous page used same information. Change only the sample size from 35 to 350 in the original sample data and find a 95% confidence interval using StatCrunch. So let me go back to StatCrunch here, and I'm going to go to Options, Edit, same information, but I'm going to change the sample size to 350. I'm going to go back to a 95% confidence interval, and let's get our data for that. Sample mean is still 4.14. Notice my standard error went way down. It obviously should, right? Larger sample size means smaller standard error. So I've got 0.429, it looks like. Let's put that in here. So my standard error is 0.429. My degrees of freedom is now going to be 349. And then my confidence interval, my lower limit and upper limit have gotten a lot closer together. It's a narrower interval because you've got a smaller standard error. So the two things that can affect the margin of error are your t-star value and your standard error. Those are the two things that can affect the margin of error. Just like it did back in chapter 7, the z-star and the standard error affected the size of the margin of error. So we've got 3.296, I'm going to make it 3.3 and 4.9, let's see, 3.3 and 4.98. We'll go with those numbers. So 3.30 and 4.98. So find the width of each interval. For the lower interval, let's go ahead and calculate these. So the width of the 35, and when n is 35, that gave me 6.89. So okay, let's write this down, what I'm doing. So you see what I'm doing? I'm doing 6.89 minus 1.39. So 6.89 minus 1.39 gave me a width of 5.5. And then for the other one, I'm going to do 4.98 minus 3.30. So let's see what that gives me. 4.98 minus 3.3 gives me a width of 1.68. Big difference. Which interval is wider? The n equals 35 interval. All right, so when sample size increased with all other statistics remained fixed, the interval width decreased. A smaller standard error creates a smaller margin of error and a narrower confidence interval. And I know in the assignment you're going to have some questions where they're going to ask you to consider making these changes and how that might affect the width of the interval. All right, let's take a look at this example. So we've got a couple more changes. You know what, I may skip some of this because I think you probably get the idea, and I know the video is getting kind of long here. So we'll look at some of these in class, but it's the same idea here. They're talking about same data, but if we change if we change the standard deviation. So what they're looking at in this example is reducing the standard deviation. And that's going to do the same exact thing, right? Because the standard deviation, the standard error, remember, how did we figure that out? That was the sample standard deviation divided by the square root of the sample size. So if this gets smaller, if the standard deviation gets smaller, we're going to have a smaller standard error. Let's summarize what that is right here. When a standard deviation decreased, the interval width is going to also decrease. A smaller standard deviation is going to create a smaller margin of error and a narrower confidence interval. You're going to have the same result you had earlier because the standard error would also be affected by the standard deviation for the sample. Let's see what this last question says. State whether each of the following changes would make a confidence interval wider or narrower. So just some kind of general things to think about. Changing from a 95% level to a 90% interval. Well, just in general, reducing the confidence level reduces the size of the interval, so that would make it narrower. Changing the sample size of 30 to a sample size of 20. So if we reduce the sample size, let's think about that. Smaller sample is going to reduce the standard error, right? So again, the standard error is determined by S divided by square root of n. So if we reduce the sample size, what is that going to do to this number right here? Smaller denominator means larger standard error. So a larger standard error would produce a wider interval. If you want to make a note, this would produce a larger standard error. Finally, changing a standard deviation from 3 to 2.5. So as we saw earlier, standard deviation, that would be this number right here. If we reduce the standard deviation, that's going to reduce the size of the standard error, which is going to give us a narrower interval because that's going to reduce our margin of error as well.